So after internal forces, friction is the next concept we're going to learn about and solve problems with in statics. So you may be familiar with friction from your physics class. We have static friction and we have kinetic friction. Kinetic friction happens when you have two surfaces rubbing on or sliding over each other. So if I had a box like this and it was sliding across the ground, it would be static friction that would be opposing that motion. But of course in statics, none of our systems are moving, so we're really concerned with static friction. And static friction is when, or happens when, two objects, their surfaces, are not sliding on each other. And actually, an example of static friction that surprises a lot of students is a car. If I tell someone that of a car driving along and what sort of friction is acting, they think that it is kinetic friction, because they think, oh yeah, kinetic friction happens when things are moving. That's an oversimplification. If you zoom in to this interface where the tire comes on the ground, you find that the tire is not sliding on the ground. It's not doing this. No, it's a perfect touch down and up. There's no slipping, there's no sliding on each other. So actually a car simply driving without skidding, just regular driving, that is a situation where we have static friction. So let's say we had a ground and some object resting on the ground. The first question I usually ask students is, what type of friction is acting? But this is a trick question. A lot of students, they see that definition and they see, oh yeah, no surfaces are sliding on each other, so they say, oh yeah, static friction is acting here. But no friction is acting here. Right? There's really no need for any friction to happen. All I have is my weight, the weight of this box, and my normal force. That's it. No friction needs to happen. It's when I introduce some external pushing force here, when I get the static friction that wants to keep this crate from moving. So just make sure you keep these concepts in mind. This friction section of statics is very, very conceptual, and it involves a lot of visualization. So if I came over to that crate and just blew on it a little bit, that would be a very tiny force, very tiny. So accordingly, so I have balance with my sum of the forces in the x. Accordingly, a very tiny friction force from the ground is needed. And maybe I'll bump up my force a little bit. Maybe I'll come at it and I'll sort of touch it with a feather or something. Well, that's going to be a slightly bigger force, because I'm actually touching with a physical object. But still, my frictional force is strong enough to battle that. It gets a little bit bigger to respond to that feather, but as you can see, it is perfectly balancing out that force provided by that feather. So static friction is what I like to call a responsive force. And this is not a technical term, this is just something I like to call it. And I call this because it responds to the input. Whatever I push with, the static friction will oppose it so that my crate doesn't move. Now, of course, there's a limit to this logic. If I really come in, really try hard to push this thing, of course, static friction has a limit. It can't keep growing, no matter what type of force I'm hitting it with. So there is a limit to how much force this ground crate interface can create. And that limit is given by this equation. This right here is mu s, the static friction coefficient. And this right here is the normal force. So these two things are the maximum, the biggest force that the static friction from the ground can provide. And a lot of times you'll see this equation. The static friction force will always be less than or equal to this number. So this equation describes what we've been talking about. Most of the times our static friction is going to be some small number. It's going to be whatever it needs to be to balance out our input. But of course there's a limit. And this number is that limit. Static friction can never be greater than this product pair right here. This is the maximum limit that static friction can be. This is as strong as it can be. So of course if I calculated these two numbers, whatever, and said 17, so let's say 17 newtons is the maximum static friction force that the ground can create on this crate. And let's say I come at it with, a force of 20 newtons. Of course my 20 newtons is going to beat that 17. And as a result of this, the crate will start to move to the left. So, just know that this is the maximum force that static friction can produce. So we have mu s here. This is going to be a constant that usually will be given to you, and it depends on what surfaces are at play here. For instance, if I had like rubber on wood here, for instance, rubber is a very lots of friction material, so this will probably be a big number. But instead, let's say I had, who knows, like plastic on some ice surface, it's going to be a lot easier to slide that plastic across that ice. So the mu s for the plastic ice interface would be a lot smaller. And also we see that this maximum limit depends on the normal force. So for instance, let's say I put some other stuff on this crate here. What that's going to do is it's going to increase that normal force. And what that really means is that these two surfaces are pressing a lot harder on each other because of that. And because these two surfaces are really pressed a lot harder on each other, it creates the ability for more frictional force. So that's why the normal force affects the static friction force. So putting these masses here would actually make it harder for me to move this crate. Alright, so far we've talked about all the stuff that you should know from physics. Now we're going to bring in some stuff that is specific to statics. So if I push hard enough, that is, on this crate, two things are possible. One, the entire crate is going to translate. It's going to move. That's one possibility. The other possibility is that actually my force might be high enough such that actually cause this crate will want to rotate about this point here and tip this way. So really, there's only two possibilities. So let's look at the tipping situation. Now you got to realize, when we look at problems like this, we're sort of simplifying the normal force. In reality, when I have this crate sitting here, I mean, you've got to agree that each little point on the ground touching up on our crate is going to put some little upwards force. And when we add up all these, I mean, it's kind of like a distributed load if you think about it. If we add up all these forces, it'll equate to one single force acting right in the middle. And that's what we're used to looking at the normal force as. So, let's say I'm trying to tip the crate over. I'm going to want to apply my force here, and I'm going to increase it, and I'm going to keep increasing it. And as I keep increasing it, this crate is going to want to get closer and closer to tipping over. What that means is all these little crate ground touch interfaces here are going to start lessening their forces. They're going to start easing up on each other. They're going to even start lifting a tiny microscopic bit. What that means is these little normal forces here are going to be quite small. And they're going to be bigger as we get closer to that tipping point. So as I increase my force to the point where the crate actually begins to tip, my entire normal force is basically going to be concentrated at that tipping point. It's really going to be exactly at that tipping point right there. So this is a huge concept to make sure you are okay with before moving into the problems. If I tip this crate, the normal force is going to be concentrated at that tipping point where we rotate about. And to tip something, the force doesn't have to be at this north or this taller end. I mean, it could be here, and we could still tip it. So just keep that in mind too. I'm not saying that that our force has to be at that top end for us to tip. So now let's talk about slipping. What if we push on this crate such that it actually starts to slide this way? So you would think that our force would be a little lower. So as we push from the lower end of this crate and we keep increasing our force, our normal force will want to do a similar thing as it did last time. It's going to want to start creeping over towards this point right here. So again, that means that we're going to have less forces on the right and more forces on the left, such that all of them together sort of equivocate to one normal force that is kind of moving this way. And we'll keep increasing that force. And at some point, this force will beat out that maximum static friction force. I forgot to mention this, but in both cases, in the case of tipping and our slipping, we have that friction force that is growing. as we increase our external pushing force. So we keep increasing this force, and our normal force keeps going to the left a bit. But before this normal force gets to our left endpoint here, that is to say, before this thing tips over, my pushing force actually beats out that static friction force, and the whole entire crate begins to slide to the left. So know that when I cause something to slide, the normal force is going to be shifted over. It's not going to be all the way at the tipping point. It's not going to be at the corner, because we're not tipping here. This is the tipping situation. But it will be shifted over a little bit. And of course, static friction will be doing its very best to battle us. So at the instant that this thing just begins to move, our static friction force will be at that maximum limit that it can produce. And then the crate begins to slide. And I forgot to write over in our tipping, of course, we're going to have static friction as well. But of course, in this case, since we're not sliding, since we're just tipping, since there's no sliding here, this does not have to be the maximum. This does not have to be μSn. But when we cause the crate to slip, we'll keep increasing our pushing force. That normal force will keep inching over this way. The static friction force will keep increasing to battle us out, but it can only increase so much, and when it's at its max, our crate just begins to slip. And after that point, it is the kinetic friction that takes over, but this is static, so we don't really care about what happens after it starts to slip. So these are the concepts necessary to take down the problems in this friction, tipping, slipping section of statics. In my books, this is really all you need to know. All the concepts, all the knowledge you need. The rest is just practice, applying using common sense and envisioning tipping and which way friction is going to be and these things. It's just something you want to get a lot of practice with. But really all you need to know is, really, how does static friction work? Recognize that it has a maximum. If static friction is at its maximum, that means we're just about to slip. We're overcoming that maximum static friction force. And also you want to be aware of how this tipping and slipping thing plays out with that normal force. So the way my book teaches it is it splits up all the different types of friction problems into 3 types. But I don't see any point in doing this. I think it just adds a whole bunch of more things that you as the student have to know. And really, you don't really need to know that. You can solve all the different sorts of problems just by using this knowledge and common sense. And that's really how I like to teach. That you guys can look at a problem, play it out in your head, sort of visualize what the force is doing. Is it tipping or is it slipping and that sort of thing? And you can solve the problem based on common sense instead of having to memorize these different situations. So in the next videos, we'll do a whole bunch of practice problems with tipping and slipping. I hope this video made sense. If you have any questions, please post them in the comments.